To our chat presentation Turing machine design. Myself, Manjit, reach number 100. So, and with me are my teammates Ish and Abhinav. So today we are going to dissecting a complex Turing machine. So this machine is designed to solve a very specific computational problem, which requires comparison and conditional logic. So let's see the problem understanding. A Turing machine or a TM is the most fundamental of computation. So it defines what an algorithm can do and cannot do. So it is essentially a theoretical device that follows simple rules to perform complex calculations. So the specific problem our machine is designed to solve is a form of a conditional arithmetic on two numbers called x and let's say x and y. So which are input as sequence of ones on the tape. So the machine must compare x and y, and if then executes one of two calculations, x minus y, if x is greater than y, or x 2y if x is less than y. So the plan to solve this. So we get there are different phases of the plan, like matching and comparison. So the machine system moves its head back and forth, matching the ones of x against the ones of y. It uses temporary markers like x and capital X and capital Y to track which ones have already been paid up. Um, this determines the condition x greater than y or x less than y. The next phase is like execution cleanup. Based on the comparison results, the machine executes the final calculation x minus y or 2y and then performs a vital cleanup step, converting all these temporary x and y's markers back into ones of the for the final output. So let's talk about the uh, transition table. So now, how does a simple machine executes this complex plan with such a precision, with such precision? So the answer is transition table. We use transition table for that. So this table, which looks like bit massive spreadsheet kind of. So is the machine it's like entire program or complete set of all the instructions. So this table's job is to uh, define every possible action that a machine can take by answering a single question like what if I am in this state, if I'm reading this symbol, what should I do next, etc. So the rows of this machine is the current state, the q0, q1, and the dots, etc., and the descriptions, and the columns are the possible symbols it can read on the tape like 0, 1, X, Y, or the blanks we can see over there in the transition table. So every cell where a row or a column needs hold the precise instructions, change state, uh, write new symbols, move direction, left or right. So the single table is ultimate source of the truth of for the machine. It detects every move from start to the halt state of the transition table. Now we'll move on to the next formality and description. Abhinav will be explaining about it.
Good evening, ma'am. I am Abhinav and I'll explain the formal TM descriptions. So we have the Q naught start state, and the Q naught start state will start and compare X and Y. So if X so if X is greater than Y, we'll go with this condition, and if X is lesser than or equal to Y, we'll go with Y. So in the Q1 state, we find the first unmarked Y, and in the Q2 state, we move on to find the return to find the next X. Q2 state and Q3 state, we'll check if the condition X is greater than Y, and if it is, we'll restore marks, prepare to append, and clean up. No, prepare to append. Q5 and Q6 is checking the condition X is greater than Y and clean up. Q7 is finding Y to append, and Q8 state is appending 1 to that current state, and Q9 is the final cleanup, and Q10 is the halt state. And now Yash will explain the numericals that we have here.
Hello, ma'am. My name is Yashwant. This is number 87. So I'll be explaining the example. So here for the example one, we can see that x is given as 3 and y is given as 2. So the input would be 3 ones, 0, 1, 1. And through the condition that is stated in the question, we get x plus 2y. So using that formula, we find that x is greater than y. So using the condition and the statement, we get 1 power x, which means 7 ones. So coming to the first state, uh, we convert the first one to an x. So it will, after the first loop, it will turn into, the tape turns into x 1 1 0 1 1, and after the state goes to the extreme right hand side, it turns into x 1 1 0 y 1. After the second loop, the tape turns into x 1 0 y y. Now the machine is looking for q1. Machine in Q1 is looking Y to mark, but then we find that there is no Y after the in the right hand side. So we must fill in a blank because it ran out of Ys. Now this triggers a X is greater than Y logic. The machine follows the path to create state Q5, where it erases all the marks of X's present in the tape. Now, if we keep following the trace, we end up with the machine giving us 7 ones. So x is 3 and y is equal to 2. The output that we get is 7 ones. And if we were to take example 2, we find that the condition goes that y is greater than x. So here the condition for y greater than x is y, as given in the question itself. So the input we get is 2 ones, 0 5 ones. And as expected, we get y as the number of ones, so which is 5. So again, as we look at the example, the in the first loop we end up getting x1 0y 1 1 1 1 as the machine goes through the tape. And after through the second loop, we get XX 0 YY 1 1 1. Now the machine is looking for Q1, looking for X to mark. Since there are less number of X, we find that 0 is a separator and it ran out of X's to mark in the left hand side. So this triggers the logic of where X is lesser than or equal to Y, sending it to state Q4 where we are preparing to append. Now the machine goes into its append phases, which was as mentioned by Abhinav, Q6, Q7, and Q8. So this Turing machine is a compactor that runs on two different calculations based on the result that we want, ma'am, because it has two different types of conditions. So by combining the state diagram as given as and the transition set rules that we have created, we can design a Turing machine that not only compares the values between different executes on different and complex calculations based on the result.